start?
Okay, let me start first. Assalamu alaikum. On behalf of our Chancellor, Professor Dr. Sashain Hamadi, and the University Committee, we are welcoming you and thank you deeply for participating in visiting the Professor program and giving these interesting lectures. Thank you to you and thank you to all the professors from the university for participating in this program.
Okay. Nice.
Thank you, sir. Yeah. You can start your lecture by introducing yourself and your lecture and start continue. Thank you to you.
Thanks a lot. Actually, I'm Alireza Faridhosseini, PhD from University of Arizona in hydrology and remote sensing, and also associate prof in Firdaus University of Mashhad in water engineering department. And as you can see, my topic will be fundamentals of remote sensing, or sort of basic stuff in remote sensing. For today, as of June 12, 2021, for now around 12 to maximum 2 o'clock. Is definitely, I try to less than 2 hours, maybe 1.5 hours, my presentation will be. And my email address, if you have any question or concern or comment, is farid-h@un.ac.ir. For this fundamentals of remote sensing presentation, I'm sort of actually introduce one of the references which is really useful and you can just use or buy online. Is remote sensing models and methods for image processing. Is sort of from fundamental or basic to advanced, and is the author is Robert A. Schwengert, and this is like 3rd edition, and maybe 4th edition is now available. I'm not sure, but I have also this as a PDF online, and if someone is interested, I can just email this book as a PDF, the 3rd edition. The introduction is a definition of remote sensing and its importance, history of remote sensing. As you can see, the term remote sensing in the early 1960s by geographers in the Office of Naval Research in the United States to apply to the information derived from photographic and non-photographic instruments. And as you can see, we have at least 3 definitions of remote sensing, 1, 2, 3. But the most popular definition is by Qasim Asrar in 1989 from Theory and Applications of Optical Remote Sensing, which he defined acquisition of information about the condition and or the state of a target by a sensor that is not in direct physical contact with it. It means 3 critical components to remote sensing, to definition of Qasim Asrar. 1, target. 2, sensor. 3, collection of information and inference or interpret of target properties to define and see what's going on for these properties of target. Without all of these components, you are not doing remote sensing. Okay, what's the target? Target is the thing you want to get information about. Without a target, there is no remote sensing problem. Anything can be target. For example, sun, Earth's surface, especially Earth's surface, ocean floor, or missile launch site. Number 2 or component, number 2 or second component is sensors. Devices that collect the energy from the target. Sensors can be passive or active, which I'm going to show in next slide. What does it mean, passive or active? Active sensors. The most important example for active sensors are radar and LiDAR. LiDAR is laser or light detecting. And passive sensors, as example, the most important natural passive sensor will be eye, and then camera or radiometer. Okay, active and passive sensors, as the last slide which I mentioned. At the top you can see is the passive sensor. We have one source, which is mostly sun, just emit the radiation or the light radiation to the surface, and from the Earth's surface or any surface reflect to the sensor. Means sensor just get the reflected light or reflected radiation, or emitted from the surface. Reflected, it means for short wavelength, and emitted means for long wavelength. And this is like the passive, like our eye never ever send the radiation, always get the radiation. If there is a light, we can see everything, all reflections. If there is no light, definitely it's totally dark. For active sensor, as you can see in the below figure, the sensor will be send the radiation to the surface, and then surface reflect to the sensor. Means two-way direction, send and then receive. This is the active, like LiDAR, radar. Any other type of satellites which we have, especially in natural resources, mostly they are passive, just receive the reflected light mostly from sun. This is active and passive sensors. Okay, just this is sort of the examples of active sensors. Radar is one of the most important example of an active system. Radar mostly can use in aircraft in distinguishing or determination of raindrops in clouds, and also the surface soil moisture now. The satellite we can just name is like this map. LiDAR used for 4 different topics. 1 for topography, like digital elevation model. 2 for 3D structure of vegetation. 3 for distinguishing the difference between clouds and aerosols. And number 4 for bathymetric river or channel measurements, like depth. The SODAR using the sound waves mostly just relies on index of refraction changes in the atmosphere, and sort of just used to measure profiles of temperature and winds, the sound waves, as one of the active sensors as example. Passive versus active, there are several reasons one would want to use active systems. In theory, you know the source is sensor, so it is easier to infer target properties. Allows the user to use wavelengths which are not available to passive systems. Radio waves can penetrate clouds. Day and night is irrelevant. This is very important for active, because for passive mostly you should have sun as a source. Also, there are several reasons to use passive systems. Passive mostly in visible and near infrared, and a little bit in shortwave and thermal infrared. And as we can see, the biggest problem for active systems versus passive is the size, power usage, complexity, and expensive when compared to passive sensors. And the importance of remote sensing can quickly give us information regarding the environment, improve our ability to inventory and manage the Earth's resources, help with interplanetary studies. Remote sensing allows us to do these tasks quickly and without extensive labor in field. Natural disaster assessment, agricultural improvements, geologic studies, meteorological improvements, and astronomic studies. Okay, in natural resources, the usage of satellites or applications, they are in climate change, geology, oceanography, meteorology, natural resources and environment, and also hydrology, like surface hydrology and groundwater. The history of remote sensing, the first aerial photo took by Nader in Paris in 1859, and then by plane in Italy in, you can see here, in probably 1904. The first, let me see here, yeah. The first satellite just made by Soviet Union, or now Russia. The name was Sputnik 1 in October 4, 1957, and the size is like basketball ball, which the same size. The weight is 83 kilogram, and in two wavelengths, 20 and 40 megahertz, in one elliptical direction or orbit, and the distance from Earth's surface 250 kilometers, and for almost 100 minutes just turn around the Earth on that time. The natural resources satellites by Americans in 1972, the Gemini series of satellites, Landsat right now, from Landsat 1 to Landsat 8, which mostly or purely just used for natural resources like vegetation, like soil, like sometimes I can say for cloud, and anything in terms of agriculture and environment on the Earth. This is sort of the first natural resources satellite. In 1980s and 1990s, remote sensing platforms became larger and more complex. Fewer missions were flown due to budgetary constraints. These missions became larger with more sensors on board each platform. The Landsat 7 and Tra launched in 1999, Hubble Space Telescope. And in the late 1990s and 2000, emphasis is shifted toward smaller, more focused missions and also active sensors, means faster, better, cheaper philosophy. Multiple smaller missions to Mars, hyperspectral and LiDAR became more relevant, and also working on GIS and visualization tools. It means on remote sensing softwares like ERDAS, ENVI, and etc. Okay, I'm going to explain what's the resolution in next slides, but high resolution means small pixel size. As you can see, the examples for terrestrial remote sensing includes Landsat, Spot, Aster, IRS, Iconos, and QuickBird. Landsat is American, Spot is French, Aster is Japanese and American satellite, IRS is Indian, Iconos and QuickBird, they are American satellites. You can see the pixel size in first column is meter, 80, 30, for example, 20, 10, 15, etc. And then blue, green, red, near infrared, shortwave, infrared, thermal. These are electromagnetic radiations from short to long wavelength. Is nanometer and micrometer. As you can see, each satellite covers this electromagnetic wavelength area. We go to medium and coarse resolution. Resolution means spatial resolution sensors. As you can see, the pixel size larger and larger, which is famous, no AVHRR, used a lot, MODIS, and that's it. This is sort of like medium and coarse resolution. And also you can see the spectral resolution, the area of electromagnetic wavelength which they cover, from visible to thermal, which is long infrared, long wave infrared. Okay. The next slide is talking about the energy. The energy is two phases, quantum and wave in nature. The shorter wavelengths are dominated by the quantum nature of light, the longer wavelengths by the wave nature of energy. As you can see, from short wavelength to long wavelength, from left to right, the first one as the shortest, gamma rays, X-rays, which we have not used them in remote sensing, and then ultraviolet, same. The starting of electromagnetic radiation comes from visible, which consists of three bands: blue, green, red, visible spectrum. And then the next one, when goes to longer, is infrared. It means near, middle, thermal. After that is radar, which is microwave, and that's it. And then radio, TV, UHF, VHF, we're not going to use in remote sensing. Okay, visible. The visible is from 0.4 to 0.7 micrometer. The shortest wavelength or color belongs to blue, as you can see, and then in the middle side of this visible is green, and the long wavelength is red. The infrared, as you can see here, for range of infrared from near to long or thermal, is from 0.7 to 1,000 micrometer. And for near infrared, is from 0.7 to 1.3 micrometer. For short wave infrared or middle range of infrared is from 1.3 to 8 micrometer, and thermal infrared is from 8 to 15 micrometer is the range of wavelength. The next, or the longest next to radio and TV is microwave, especially for soil moisture and meteorology, like raindrops in cloud, used a lot. The wavelength for this microwave is from 1 millimeter to 1 meter. They can penetrate the atmosphere and cloud, and in any climate condition we can use them. No effect from rain. We can use in airplane business, in airport business for guiding the airplanes. As I mentioned, for meteorology, especially for raindrops in cloud, and also soil moisture, the surface, from surface to minus 10 centimeters. And we have different bands, which is not our discussion right now for these different bands in microwave. But like infrared and visible, we have different categories of microwave, from short to long. Resolution. Any questions so far? Any question?
لا دكتور.
Can you hear me? Okay. I suppose no question. Resolution, just I'm gonna continue. Remote sensing sensors, they have 4 basic characteristics or resolutions: spatial, spectral, temporal, and radiometric resolutions. Temporal, it means how long the sensor is turned on to look at the sample or target. It means integration time of a single sample or repeat time of the sensor. This is temporal resolution from GOES satellite on top of the whole United States, and for visible, and the temporal resolution is 8-hour period. But now we have to half an hour period for temporal resolution for different satellites. Radiometric resolution, more commonly called the dynamic range of the system, is sort of hardware of the satellite, minimum and maximum energy levels that can be measured by sensor. And I'm going to explain this more in a few slides. Spectral resolution, entire range of wavelengths or bands covered. Two types of spectral resolution we have, especially for passive sensors. One, multispectral, which the number of bands is less than or equal 10, or some books say 30, and hyperspectral, which is more than 30 bands. Bands means, for example, band blue, band red, band green. This is belong to visible. And then near infrared band, thermal band. This is sort of a spectral resolution. The spectral resolution for Landsat ETN plus bands 1, 2, 3, 4, 5, and 7. As you can see the images, each band can get some reflection from the target. Some targets more reflect, some target less reflect in a specific band. It depends on the band and also getting or receiving the reflection from different objects on the Earth's surface. Spatial resolution, two components. One is cross-track and the long-track direction, which calls SWAT width. Is sort of, and also the other called pixel, or ground instantaneous field of view, or ground sample distance, or ground sample interval. All means pixel. All means pixel. Okay? Can you hear me? Still there? Still there? Okay, good. Okay, for this spatial resolution, I have an example. As you can see, the right side, the pixel size is 30 meters, and definitely better image we have, because more detail we can get. The left side is modest 500-meter spatial resolution, definitely more blur and less detail, and sort of we cannot get more detail from this image. Okay, there is no best answer to what the spatial, temporal, spectral, and radiometric resolutions of the system should be. Typically, a compromise between all factors must be made to get the desired data. For example, consider the case where we want higher spatial resolution from a satellite. Okay, it depends on your application, it depends on your target, it depends on your budget, which resolution you should select, high or low, in terms of 4 resolutions which I explained. Satellite orbits. Okay, regarding the satellite orbits, orbit of the sensor affects the temporal and spatial resolution of the sensor, as well as the size, weight, cost of the system. Typical orbits are here, geostationary on top of the equator and on height of 36,000 kilometers. Second, the polar orbiting from north to south pole. The height is less than 1,000 kilometers, and the short temporal resolution, the example is NOAA. For example of this is GOES 8, 9, and 10. Okay, and parameters describing orbit or height, inclination, repeat period, and crossing time. Okay. Regarding the dynamic range or radiometric resolution, in remote sensing, we have analog and digital data collection. In the past, the aerial photos or photographic techniques is based on analog, which we have film on the system. In digital remote sensing is opposite side of analog. Definitely we have row and column, we have pixel, and that's the sort of like the digital element, and inside each pixel we have digital number, or the number which mostly shows the amount of reflected energy from the target. Okay, based on this digital number, we want to know the satellite, the bit of the satellite system is 6, 8, 10, 12, 14, or 16. Mostly 8-bit system is the original, which the number of DNs in 8-bit system is 2 power of 8, and the range, which is minimum energy level to maximum, is from 0, means no energy reflected, to 2 power of 8 minus 1. For first one is 256, the number of DNs get the energy levels, and the range for DN from 0 to 255. As we improve our system, especially for active sensors, we increase the bit system from 8 to 10, 12, 14, and now 16, especially for active sensors. Data visualization, we combine the previous two topics to understand the idea of this concept. The detector, which I'm going to explain in next slides, converts the energy from our target to an analog signal, which is converted to a digital output, pixel and image, which is used by an image display tool to put on a computer screen. Sometimes the hardest part is getting the image into software that allows manipulation of the data. The format of the image data in remote sensing is like HDF, binary, ASCII, and etc. Examples of software packages in remote sensing, which we have, the first one is Idrisi, the middle one is ERDAS, and now NV. These are commercial software packages for image processing. The next topic is spectral signatures. Look at how an object or target reflects energy as a function of wavelength. It's critical in remote sensing. A spectral signature is the idea that a given material has a spectral reflectance which distinguishes from other objects on the Earth surface. As an example, here we have the reflectance on y-axis and wavelength on x-axis, percentage and micrometer. We have green leaves and water around visible area from 0.3 to 0.8 micrometer. The water is the highest reflectance for visible is on the blue area. That's the reason we can see the water as a blue color. For green leaves, on the visible on green band is the highest reflectance, and then near infrared. That's the reason our eye can see the green leaves as green color. This is spectral signature. With the spectral signature, we can differentiate between different types of vegetation. For example, coniferous forest, broadleaf forest, and grass. The grass is the highest reflectance versus the other two types of forest. Based on reflectance versus wavelength, we can just distinguish the cold and dead condition of a plant. Less reflectance means dead. The highest reflectance belongs to healthy plant. Also, based on a spectral signature, we can just distinguish the water stress on leaves. The blue color on the below, which has the lowest reflectance, means it has 88% water stress. And the green one, which has the highest reflectance in a spectral signature, has the lowest water stress on the leaves, almost 0%. We can distinguish between these materials based on a spectral signature. And the last one, again, a spectral signature based on leaf area index, where soil we have, and then the vegetation for leaf area index from 1.6 to 4.4, which means when LAI increases, reflectance means increases too. Okay, two examples of radiometric setups we show here. Left side, as you can see, we have source, transmission medium, object, and then sensor. Sensor has optical system, detector, signal processing, and then image or output, which is digital. The second radiometric setup is right-hand side. As you can see, source, transmission medium, and target or object inside the transmission medium, like raindrop in atmosphere or cloud, or aerosols in atmosphere. Atmosphere is transmission medium, and then sensor, the different elements of the sensor. Two setups for radiometric in remote sensing. Okay, based on the transmission medium, which is atmosphere, atmosphere is divided into 4 sections according to temperature structure. The lowest is troposphere, from surface or 0 to, I can say, 16 kilometers. This is the most important part of transmission medium for remote sensing, is troposphere. And then stratosphere, mesosphere, and the highest thermosphere. In troposphere, the first one from surface contains 75% of Earth's atmosphere. Stratosphere, which is the next one, from 10 to 50, mostly ozone, O3, mesosphere 50 to 80 kilometers, and above 80 to 100 is thermosphere, which is not related to remote sensing. In first one, troposphere, we have aerosols. Aerosols are anything suspended in air. Most often, the term refers to dust in the atmosphere, which is really, really important these days for remote sensing studies. Also applies to liquid water, particulate matter, airplanes, etc. Primary source of aerosols is the Earth's surface. Residence time of aerosols, 7 days. Size of most aerosols is between 0.2 and 5 micrometers. Larger aerosols fall due to gravity, smaller just make larger particles. The two effects of atmosphere on solar radiation or electromagnetic radiation is one, is absorption. Second, the number 2 is scattering. Scattering is the broad term used to describe the interaction of electromagnetic radiation with particles. If the particles are too small, we call Rayleigh scattering. If mid-size, we call my scattering. If it's large, we call non-selective scattering. Because of Rayleigh or Rayleigh scattering, the sky is blue because it's most scattering happens for blue band. And if we have dust, because dust has my scattering is mid-size of particles. The absorption, the second one, is a form of attenuation where radiation is converted from one form to another, from light to thermal. Occurs mostly in infraportions, near, mid, or shortwave. There is absorption in the visible and near infrared. We can see in the below figure. The y-axis is atmospheric transmittance. The x-axis is wavelength. We have drop in transmittance because of O2 and water vapor. They absorb the solar radiation. This is important. Optical depth, another definition in atmosphere or transmission medium, describes the attenuation along a path in the atmosphere. Depends on the amount of material in the atmosphere and the type of material and wavelength of interest. Optical depth can be divided into absorption and scattering components, which summation together give the total optical depth. Scattering, absorption. Scattering, as I said, by aerosols and molecules in atmosphere. Absorption, water vapor, ozone, and dioxide. Dioxide, carbon, and oxygen absorb this solar or electromagnetic radiation in the atmosphere. Okay, the next slide in remote sensing as a fundamental definitions, there are signal and noise in image processing. Signal is the part of the output that is desired and rest is noise. Detector output will consist of a useful portion signal and the rest, which is not useful, is noise. Depends on the satellite, sensor, measurement, application. And atmospheric, for example, medium is one of the sources mostly for produce noise. And sometimes the atmospheric transmission or this medium can be also signal. Scanning systems. Okay, before explaining the scanning systems, I just mentioned about the spatial resolution as I defined. The spacing between pixels on the ground is the ground sample interval, or GSI, or the ground sampling distance. The cross-track and in or along track are determined by the cross-track and in-track GIFOVs. Cross-track means the whole width of one image from sensor. The along track means the length of whole image of one sensor, because the image looks like mostly square or rectangular, sometimes equal, sometimes not. We have two different scanning systems, one whisk broom, two push broom. In a whisk broom scanning system is similar in philosophy to the paddle wheel approach, except the mirror sweeps back and forth. We have one mirror is one of the elements in optical system for satellite or sensor, and also one single detector which saves this reflected energy. Approach is common to narrow SWOT sensors since it reduces wasted portions of the scan line. Mechanically more complex since you must stop the mirror and send it back in the other direction. The example for this type of scanning is Landsat TM and ETM Plus. Push broom. Instead of one single detector, we have array of detectors. Push broom systems rely on the detectors, not detector, to give the cross-track sampling, not a scanning system in the strictest sense, since there are no moving parts creating the image. There is no mirror sweep. Smaller, advantage. Lighter, less failure. Used primarily for small SWOT widths, since large SWOTs would require a large number of detectors. The example spot, Aster, ALI. These are examples which they use the push broom scanning system. Okay. Types of surfaces in remote sensing. Mostly Earth surfaces. We will come across a specular and diffuse surfaces in remote sensing. For a specular surface like mirror, one incident, one reflected from the surface. Example, the famous or most famous is mirror or water surface in river or lake. If we have some mixed material, for example, in the mirror or in surface of water, we have near specular type of surface. The other surface is diffuse surfaces, just diffuse in half a circle angle or 180 when the surface is Lambertian. For example, we have a forest with same height of trees. When the incident solar radiation comes to this same size of forest trees, we have diffuse surface or fully Lambertian surface. If this height of trees, they are not the same, we have near Lambertian surface. This is very common used for Earth surface in computational or physical relationships or formulas which we have in remote sensing. Any question? Okay. Question?
No, Doctor.
Okay. Components of Earth observing systems or digital sensors, not analog. Most satellite systems are now electro-optical systems, not field-based. Also, in real life, not anymore use the cameras with film. Everything is based on digital, like our mobile phones, the camera and the rest. And all EO systems have similar characteristics. We have the ground surface as a target or object of interest, reflected light or radiation from surface, reach to optical system, which is camera, and then energy just past the spectral selection, which means the band of system, visible, near-infrared, thermal, shortwave, or microwave, and then save in detector, which is array, And then this detector just convert or transfer the energy to the analog to digital conversion system. And then when convert to pre-digital conversion, we have the pre-processing, which I'm going to explain in the last slides. And then after pre-processing of one image in remote sensing, we have the image itself, which is ready to use for us. Mostly, we just use the image, the final product in remote sensing. We are not going to deal with the previous steps. That's not our job. That's our job, just use the image. Their job, like NASA or the other agencies, just preparation of these steps, and just their job is using these steps, not us. Detectors. In optical system, we have the camera. I'm not going in detail in camera because this is sort of more physical and mechanical term. The detector is the part of the sensor in satellite that converts the incident energy to an electronic signal. The selection of the detector is determined by the requirements for spectral response, speed of response, signal to noise ratio, linearity, dynamic range, cost, availability, size. Response or responsivity refers to the ability of the detector to convert the incident energy from target into a usable output. Low response is not good anymore these days. Implies that either the output is low for a given input radiant flux or a lot of radiant flux is needed to obtain a useful signal. Radiant flux means reflected energy from surface. All detectors fall broadly within the two types of quantum-based detectors or thermal-based detectors. The quantum-based detectors, which is used a lot for most of satellites, especially the passive sensors. Photons interact directly with the electronic energy levels within the detector to produce free carriers. The advantages: high sensitivity, fast response. The human eye and camera film are simple examples of quantum detectors, or mobiles. Photoconductive solid-state detectors are based upon the idea that incident photons provide the energy required to free valence electrons. The examples are charged coupled devices, silicon photodiodes, phototransistors. They are examples of quantum-based detectors in remote sensing. Thermal detectors operate on the concept that as an object absorbs, not reflects, absorbs energy, its temperature changes. Mostly used for long wavelength, especially for thermal infrared. Slow response time, one of the disadvantage, extended spectral range. This is sort of the first one, slow response, is disadvantage. The second one, extended spectral range, is advantage. Responsivity is constant with wavelength, advantage. Thermocouple has a change in voltage, disadvantage. Currently not practical for most remote sensing applications because of a slow response time. The biggest disadvantage of this system or detectors, thermal detectors. But in the past, especially in Landsat, they use for thermal band. Okay, here we have the pre-processing and image rectification. Now, these days, we are going to do this part, especially in Iran, because over there, for example, in the US or Europe, we have a team inside the agency or our department to do this part image rectification. But our students or ourselves, we don't have, or we have a lack to have the technical person to do this. What is the image rectification in remote sensing? One, noise removal. I explained what's the signal and noise. Noise removal. Sometimes we have missing data, is the noise. Sometimes we have not applicable data, which is noise. We have to deal with this part. Sort of write the code, delete or drop or eliminate this part from the data or image, and then this is image rectification, and then use the image after removing that null or NaN part of image, which is not measuring. I had this problem with LiDAR when I used for my PhD dissertation. It sort of actually just took my time for a few months to write a code or codes for noise removal from LiDAR system, which is active sensor for measuring the 3D structure of forest, trees, or vegetation. Number two, radiometric calibration, conversion of DNs to a radiance value, which can be compared from day to day and sensor to sensor. Mostly, for radiometric calibration, we convert the energy to DN. I explained what's the DN. DN, digital number, the value in each pixel of one digital image. For this conversion, we have linear conversion or non-linear conversion, which it sort of contains several sessions to see what's the linear or non-linear conversion, mostly radians to DN. Number three, atmospheric corrections through the use of either physical models of the atmosphere or ground calibration targets, variation in atmospheric conditions. Atmospheric corrections means, in general, scattering or absorption, which I explained. Sometimes scattering causes a fake cloud in one image. You have to correct them. It's not cloud. Here, this is my scattering on over Oman Sea and Pakistan. This is not cloud. This is atmospheric correction for this image. And this atmospheric correction is one of the hardest parts in pre-processing or image rectification. Because if we want to use the physical model, mostly they are in Fortran language. They are hard to learn, and training takes time. And sometimes based on the physical parameters or characteristics, you have to write a code to do the atmospheric corrections. Number four in pre-processing is geometric rectification. The images, mostly, they are not sort of match to the real image on the Earth. You have to register it based on the ground control points or GCPs to match the image with reality. This geometric rectification, we have different models or methodology, such as bilinear, such as cubic convolution, to do this, to match our image with real ground, the 4 points to 4 points on the ground. Here, the GPS used a lot for this geometric rectification. After pre-processing, which sort of have 4 steps, as I explained briefly, we have image enhancement. This is sort of like image processing, not pre-processing. Image processing includes Contrast stretching, modification of the original DN range to improve overall contrast and interpretability or enhance a particular range of DN values. Most of the time when you change the DN values or range, just extend from whatever it is to 0 and 2 power of DN minus 1, we can just see some objects on the Earth better and more clear with this contrast or DN stretching. This technique we have in softwares such as NV or ERDAS or Idrisi as Prepper or as a method which we can just select and then use on our image to see what's going on. Is it better in terms of contrast or not? Number 2 for image processing or enhancement is edge enhancement and spatial filtering. Mostly use the convolution filters, low pass or high pass filters. The high pass filters just show the edges of one image. The low pass shows the big objects on the image, which has large areas. This high pass and low pass filter we have on remote sensing softwares or packages like NB. Just select and see what's going on, what's happening on the image. Number 3, band rationing, used to highlight the spectral contrast between surface materials. For example, a ratio of the near infrared to red is good for showing differences in vegetation. Just use the spectral resolution of one sensor. Or NDVI, normalized difference vegetation index, near infrared minus red divided by near infrared plus red, which is developed for vegetation assessment. This NDVI used a lot to see we have vegetation on the image or not, versus, for example, water surface versus soil surface. High values of NDVI means greater density or amount of active vegetation. Low means no vegetation. The range is from 0 to 1, this NDVI. PCA is sort of just linear transformation of spectral bands, which sort of can use for image enhancement. Is so complicated methodology for image enhancement. Mostly nobody used these days this PCA technique for image processing or image analysis. Image classification used a lot. 2 types of classifications we have in remote sensing. The first one is unsupervised classification. We as a user encounter, no act on computer classification. Computer itself distinguishes the classes in the image. And the procedural methodology is called clustering in unsupervised classification. Everything is based on computer decision, algorithm decision, or software decision. Sometimes we use this technique for image classification. Classification means, for example, some part of one image has agriculture site, soil, surface, or bare soil, forest, city, water, and etc. This is image classification, different classes in one image, used a lot as land use map these days. Because land use map change every time, sort of every month, every year, every 6 months. You have to update based on this technique. The second category of image classification is supervised classification. Requires me or you as a user to train the computer and learn the computer for different classes. We call that the train sites. Who gave or give these train classes? We, user, the human. The analyst trains the computer to classify image pixels based on samples the analyst specifies from training areas. We have to go to the site, see the different classes, take the GPS points, the differential GPS points. For example, you have 5 or 6 classes, come and sit in front of computer, just give these points, just get the training pixels, and based on these known pixels, just classify the unknown pixels based on this supervised classification. We have at least 3 techniques or algorithms in supervised classification. The most famous one is maximum likelihood supervised classification algorithm, used a lot. After we classify, we have the map, the land use map or the classified map. We have to do the accuracy assessment. The accuracy assessment means when compare this digital land use map to reality, go to the field, see how many pixels they are error in terms of classes, how many they are correct in terms of classes, and get the overall accuracy. If the overall accuracy, for example, is above the 70%, means our classification is acceptable. Is less, we have to repeat the supervised classification or change the algorithm of supervised classification, or classification itself from supervised goes to unsupervised. The other technique in image processing is data merging and integration. It entails spatially co-registering different bands from different sensors. It's so common these days, or non-sensor data. Combine different data sets, different sensors, sensor and field measurements. One example of this would be merging spectral and terrain or elevation data to better classify forest species. Means we have digital elevation model from terrain combined with spectral, like visible, and classify the forest species. This is used a lot in remote sensing. Change detection or multi-temporal analysis is a very significant aspect of remote sensing, especially for geology, especially for mineral components. Change detection can be a fairly straightforward job for interpreters evaluating large-scale air photos, but visual comparison of air photos can be slow, tiring, and is subject to numerous errors of omission. Computer-assisted methods are often used to correlate and compare 2 sets of images to identify changes. Data preprocessing is particularly important in multi-temporal or multi-sensor studies so that the radiometric, atmospheric, and geometric characteristics of the data set are normalized. Besides aerial photos, satellite sensors, active and passive sensors, these days we use a lot the drones and the data from drones, because the drones itself has different type of data, different type of image processing, different type of technique compared to other sensors. For platform, we have satellite or space-borne platform. We have airborne platform, especially for LiDAR. We have mobile platform, especially for LiDAR again. Also, we have the ground platform, like the survey cameras which we used on the field and on the ground. this is different type of platforms which we use in remote sensing. That's all for sort of basic or fundamentals of remote sensing. I have more and more stuff which is deeply goes inside to remote sensing. Different researchers use different sensors, active, passive, drone, airborne, spaceborne. If someone is interested, I can just pass the papers and our works, which is almost 20 years of work on the remote sensing and natural resources, especially water stuff. Any question? I'm ready to answer for your questions, please. Thank you so much. Question? Can you hear me? I'm here to answer your questions. If any question,
Any question?
please.
اوكي ثانك يو دكتور عليرزا. طلاب اكو سؤال اخواننا الاساتذه؟ اي سؤال تحبون تسالون الاستاذ حول الريموت سensing؟ Okay, Dr. Alireza, you just can drop your email in chat.
Sure.
And the students will email you definitely, and the faculty member for all the questions, and that you can answer directly on email.
No problem.
And let me introduce myself again. I am Dr. Kian, the manager of the Information Technology and Communication Center at the University of Basrah. On behalf of Vice Chancellor for Scientific Affairs and all the university members, introduce our deep thanks to you and to your university for participating in this program, and thank you for your efforts and your sharing information. Thank you to you.
You're very welcome, and thanks again, and thanks a lot for you guys for your attention.
Thank you very much to you. Thank you.
Thanks. Bye-bye.
باي باي.
Bye.
طلابنا هذا الايميل مالت الاستاذ الزائر، وهسه راح ادز لكم الرابط مالت الحضور ايضا حتى تسجلون الحضور عليه. هذا رابط الحضور حتى تسجلون حضوركم وتكتبون ملاحظاتكم ايضا بالرابط. والمسج اللي قبله هي محاضره الاستاذ الزائر، الايميل الاستاذ الزائر. تقدرون اذا واحد عنده اي سؤال يقدر يساله مباشره. شكرا جزيلا لكم ولحضوركم ويانا في هذه المحاضره.